Hey gang, and welcome back for another worksheet solutions walkthrough for the worksheet practice with Aldol, Michael addition, and Robinson Annulation Reactions. Okay gang, if you're watching this video, I know I say this sometimes, but actually take a deep breath. These reactions, I remember when I first learned them, you get hit with them all at once, usually in a week or so, and you're like, what the hell is going on, right? And that's okay. They're big, right? You're combining big pieces, you're cyclizing, you're attacking the fourth carbon instead of the carbonyl carbon, like what's going on? This worksheet is designed to kind of be like, hey, just so you know, here's that reaction you learned about. Now do like 5 of them. It's really meant to just reinforce the concepts, to show you this is what an aldol reaction looks like. And remember, at the end, you're gonna want that 1,3-hydroxycarbonyl. You know, it's just very structured practice. It's not meant to turn the difficult, crank the difficulty up. It's meant to be structured, productive, get your feet underneath you, so then you can do the next worksheet that's really meant to be like, okay, all bets are off. Here are some hard problems. So if you're here, don't worry, we're getting our sea legs. I'll stop talking, we'll go through the worksheet, and hopefully by the end you'll feel much more comfortable with aldol reactions, condensations, Michael additions, and more generic 1,4 additions with the cuprates, Robinson annulations. And, I know you've seen the worksheet probably already, but hopefully my explaining it will help it sit a little bit better. So let's get after it. Okay, gang, so not really problem 1, but at least the 5 problems associated with the aldol reaction in basic conditions, both the regular reaction and the condensation. You can see I tried to squeeze them all on here, and I did a really good job of fitting it, but not spacing it out well. So if we take this first reaction up top, so maybe if you looked even scanned just down here, you're going to see different conditions for kinetic and thermodynamic enolates. But if there wasn't going to be a discrepancy as to which way to form the enolate, I just threw in a base. So as you can see up here, right, there's no difference between a thermo and a kinetic enolate that we could form here, so I just threw in LDA. So right off the bat, what I'll do is we can have this enolate right there. So then, second, we throw in this carbonyl that we can attack. And remember, it's the alpha carbon that is nucleophilic. The alpha carbon has the electrons. The alpha carbon is the one that will be bridging this new gap, this new bond between the compound that was your enolate and the carbonyl you're attacking, okay? So remember, electrons swing down. It's this carbon that's saying, I'm taking the electrons in these bonds. Remember, that was the carbon that got deprotonated in the first place. It then takes the electrons, it attacks the carbonyl carbon because it's nucleophilic, and that's a good electrophile, the carbonyl carbon, and then the electrons bounce up onto this oxygen right here. You initially form a negative charge, remember, so what we can do is we reformed the carbonyl, as you can see right here, and then my dot carbon bonded to what I'm going to call my asterisk carbon. So the minute I draw a line from this dot carbon, that is now my asterisk carbon. And the asterisk carbon is a part of a chain that has another 2 carbons on it. And you can also see there's the O minus. Well, what is initially an O minus, but there's going to be something that will quench the negative charge. A proton from water, for example. So you don't stick with this product. You'll end up getting an OH, and you did your aldol reaction, right? This is not a condensation, just the regular reaction correctly. If you end up with a 1,3-hydroxycarbonyl, remember, you get an alcohol, you call it a hydroxy group. When it's not your highest priority functional group, hydroxy, and then a carbonyl, and there's 3 spaces apart. Okay, I won't go into detail for all of these, but that much detail, but that is the general gist of what we're doing here. So down here, now you can see why all this enolate practice came in, because if you got hung up on the fact you don't know which way you're going to form your enolate, doing this problem, it's going to be very difficult. So you can see we have thermodynamic enolate conditions here because small base, warmer temperature. So the enolate we initially formed looks like this. And then we attack this benzylic aldehyde, right? We're going to attack the carbonyl on benzaldehyde. So if I even drew that super small, I'll even abbreviate the ring with a pH. Electrons swing down. Carbonyl carbon takes the electrons. I'm going to do it like this. Attack goes up there. So what I hope you'll get to the point of doing is I usually like to just redraw my enolate. And I'm going to draw my methyl group straight up. You're going to see why I did that. because it's this carbon right here that I know will be my nucleophilic carbon, and I'm going to draw a line between this and what is going to be what I'm going to call my asterisk carbon. So here's my dot carbon, draw a line, there's my asterisk carbon. I know it's going to be an OH, that's how I get my 1,3-hydroxycarbonyl, and then I have the rest of the group off the asterisk, which happens to be a benzene ring here. Okay, and then my built-in check just to make sure. 1, 2, 3. Yep, did the Aldol reaction correctly. Okay, keep on chugging along. Down here you can see, okay, we have 2-butone or butone, and we have 2 steps. The first of which means we're going to be forming a kinetic enolate. We see the bigger base, we see the colder conditions. We're going to deprotonate where it's more convenient, easier for that base to reach. So this is the enolate that we form. Meaning, since we're going to be forming our enolate this way, we're going to be attacking from this carbon, and this carbon over here is the carbon we're going to be attacking. However you want to denote them, if you don't like doing dots and asterisks, you use different shapes. Or if you don't want to mark them up at all, you don't have to. I like to do it personally though. So remember, we know how the attack works. What I'm even going to do is I'm going to flip this. Oh, whoops. See, I almost made a mistake. There's my dot carbon. The next line I draw will be to my asterisk. I know I'm going to have an OH. And then off the asterisk, I have 2 methyl groups. So methyl group, methyl group. And there's my product. You want to double check? 1, 2, 3. 1,3-hydroxycarbonyl. Okay, now down here you can see a third step for each of these. And that's because, remember in base, the leaving group we have is OH. So to overcome that bad leaving group, we have to throw in extra energy to overcome for the fact that we're not kicking off the best, weakest, stablest leaving group. So if you even want to, what I like to do is I like to form my aldol and then just form the eno. Remember, you're going to have that 4-carbon system where you have the carbonyl and then the new double bond that results after you drive off the OH. So first step is that we're going to realize that we're going to be making the kinetic enolate here. We're going to be attacking from this carbon right there. We're going to be attacking this asterisk carbon right here. So if you want to think about it, our initial aldol reaction product looks like this. But we don't stay like that. Remember, this will leave when we deprotonate this position right here. It's these electrons that swing down. Something will pick up that hydrogen, that proton. So then we form this right here. The 2 methyl groups are still there, right? If you want to think about it, this is still the asterisk carbon. The asterisk carbon did not go anywhere, okay? It's just that the OH is gone, and your built-in check here is that you number from your carbonyl, starting with the oxygen this time, and you have 4 atoms in a row, and you go sp2, sp2, and then that's a carbon-oxygen double bond. Then you have a carbon-carbon, sp2, sp2 kind of in a chain. And you remember, we can call that an enone. It's like a ketone with an alkene. Or if you want to use the fancy term, you can call it an alpha-beta unsaturated carbonyl, alpha-beta unsaturated ketone, whatever you want to call it. Okay, so down here, last but not least, again, LDA, because it doesn't matter which way we form the, there's only one way to form our enolate. This is our nucleophilic carbon right there. We're going to be attacking this carbon right here. So the initial product we form looks like this. And this is going to be a little bit of a weird one, but I'll try and draw it as normally as possible. Okay, we got something like this right here. Make sure I didn't make a mistake. But remember, this will turn into a double bond, and that will force this to leave. So our final product actually looks like this. Running out of space. And again, the built-in check is 1, 2, 3, 4. Here it happens to be an alpha-beta unsaturated aldehyde, but you could still label that an enone if you wanted to, or an alpha-beta unsaturated carbonyl. Okay, gang, that is the first of the 4 sections we have. So let's chug along, moving from basic conditions to acidic. Okay, gang, rolling on into the aldol reaction in acidic environments, which we know always must go to condensations, whether there's heat included or not. That's what has to happen. So we just have 4 problems here because, we did 2 aldol condensations in base, and these are just the same thing. You just use a different nucleophile to get there, and if you're not even drawing the mechanism, the product ends up being the same. So if we take a look up here, remember, in all of these situations, we're working with enols, not enolates, because we're in acidic conditions. Our enol looks like this if we wanted to draw it out, okay? So what we got here, that's after step 1. And then here, remember, that's when we have our attack occur, right? But nothing changes. It's this carbon. Wherever you form your enol, that alpha carbon is the nucleophilic carbon. So if you want to, the same methodology applies for how we completed the reaction. That is your carbon that you'll make the bond from. It's the asterisk carbon that is going to be attached. Now, if you even want to, I know we drew the aldol product first, but if you even want to skip that, this is how I recommend kind of doing this in your head. You have your dot carbon, your nucleophilic alpha carbon from your carbonyl. You've reformed your carbonyl. And remember, we want to make that eno. We want to make that alpha beta unsaturated carbonyl. So what you can do is just, you're going to be connecting that nucleophilic alpha carbon to your asterisk, what once was a carbonyl carbon. And there you go. You've already formed this without redrawing the carbonyl, or like the alcohol, the 1,3-hydroxycarbonyl, the result of your aldol reaction. And then you just need to fill off what's off of your asterisk carbon, which is just 2 extra carbons here. So that is the product we're gonna get here. Oops, that's not actually supposed to be here. Okay, so moving on into this example, right? This is, again, it doesn't matter which way we make the enol. So what it will actually look like is this right here, okay? So we know we're gonna take our dot carbon, just the alpha carbon, the nucleophilic carbon, and we're going to attach it to this asterisk carbon. So, and it's going to go all the way to the condensation. So if we have this right here, we know that's our dot, and what I've drawn the double bond to is in fact the asterisk carbon right there. And just off of that is a benzene ring. So you could either draw the whole thing out like this, or if you even wanted to be super cool and use shorthand, you could write a line and then pH for our phenyl group, which is a lot easier to write in my opinion. Okay, so down here, you can see there's only one way for us to make this enol. It's gonna be over here, so it will look like this. Point being is that this is the carbon we are bonding from. This is the carbon here we are going to attack. So it'll be a little strange, but we got this. We have our dot carbon. I can draw a line. I know that will be my asterisk carbon. I know there's gonna be a double bond between the two, and off my asterisk carbon, I just have 2 methyl groups, okay? And last but not least, all the way down here, you can see, I'll switch back to the red. This is the enol we're going to make. This is my dot carbon. This is my asterisk carbon. So what this looks like is dot right here. The next line, the asterisk, right, we have the double bond. But remember, that is actually a carbon inside that 5-membered ring. So you just draw a pentagon right off of that, which looks a little weird, but that is the product we get. So gang, I hope you're seeing, it's really, once you get things organized, you get these relationships down, they become a little bit more comfortable, like the functional groups you learned at the beginning of jOeCHEM 1, the stuff isn't that bad. You're building on an already big organic foundation that you have. So that does it for the aldol reactions. So now we're gonna move into Michael additions and the 1,4 additions. So let's keep going. Okay gang, in this section, we're gonna be doing both Michael additions and just generic 1,4 additions. So we're working with soft nucleophiles, right? Nucleophiles that only attack, if we have an example, something like this, we can number these 1, 2, 3, and 4. Soft nucleophiles attack at the 4 position, right? Because we know that this very strong resonance contribution to the overall hybrid looks like this. We know this 4 carbon is a strong delta plus on it. So we can do these 1,4 additions, and when an enolate does it, it's specifically called a Michael addition, and when anything else does it in the 1,4 fashion, we just call it a 1,4 addition, okay? Just a quick little blast from the past. And remember, our soft nucleophiles are everything except your organolithiums, your grignards, your hydrides, your strong hydrides like LAH, anything like that. Okay, so up here, we see kinetic enolate, right? So we're going to be making our enolate like, oh boy, like this, okay? So that's to say, we're going to be bonding from this carbon right there. Now we see that we have an eno, or if you want to call it an alpha beta unsaturated carbonyl, ketone, whatever, feel free to do that. So I'm going to draw the mechanism over here just for this, just to make sure we're on the same page. And in fact, what I'm going to do, I'll do this. Okay, so remember, it's that fourth carbon that we know is partial positive because of the resonance we can draw. Sorry, this is a bit wonky. There we go. So remember, the enolate, which I'm going to draw like this for convenience, it is interested in the fourth carbon, not the carbonyl carbon like we've usually done in the past. So remember, electrons swing down, the alpha carbon, the carbon that's in charge of those electrons, reaches out and bonds with, you guessed it, the fourth carbon right here. When we do that, we have to move something or else we're going to break the golden rule, the octet rule. So we have to balance these electrons up like this. Once we do that, last but not least, we bump these electrons onto the oxygen up top, and that's a good move. We know that's fine to do that. Oxygen likes the extra negativity. So at first, you get this, and remember, so I'm going to do dot to dot here. This is what we got, and this enolate flips back to its carbonyl form. The way it does that is this swings down, and this grabs something like a proton from water, anything really. So the point of the matter is you end up with two carbonyls, and in the case of doing a Michael addition, which is a 1,4 addition with an enolate, right, you get a very characteristic 1,5 dicarbonyl, okay? So I know I took some time to explain that, but I think it was worth it. So the first product looks like this. Okay, looks like that. Erase this. So moving right along. In this next problem, okay, so here's an example of just a generic 1,4 addition, right? To call it a Michael addition, people will know what you mean, but it's not technically correct. So what you see here is a cuprate, and a cuprate is just a soft nucleophile. It's like a toned down Grignard, if you will. So what you really have when you see this is you have an eligible pH minus. This is basically a benzene ring that has a negative charge, right? Essentially looks like this. But feel free to just use pH minus. So this is interested and will attack in a 1,4 fashion. So just like the enolate, we attack at the fourth position, the electrons kick over here, this kicks up. So what you can essentially do is off of the fourth carbon, you can attach your, here it's a phenyl group, but you can attach whatever is a part of your cuprate, and then you can go right along your merry way, and you can just go ahead and realize that yes, does this look like this at first? Absolutely, but it's gonna flip to the carbonyl. So if you wanna do that and then flip it, please be my guest. But if you wanna just go for it and realize it's gonna be a carbonyl, totally. So really, you get what you started with, but you just end up attaching something at that fourth position. Okay? Now, over here. So what we see here is thermodynamic enolate conditions, right? So we're going to be forming our enolate this way. So we're going to be attacking from this position, and we're going to be doing a Michael addition, right? A 1,4 addition, but it's that specific case right here. So if you want to think about it, what you can do is you can redraw this, and that's what I'm going to go ahead and do. And I'm going to go ahead and put these two methyl groups down. This is my dot carbon. So I know this dot carbon is going to attach to this one that I've dotted down here. And that is the first, right? To finish this chain, I have 3 more carbons. So that's 1, 2, 3, 4. And it's on the third carbon that I know. So this is 1, 2, 3 alpha carbonyl. But I have a built-in check with the Michael addition, right? I should have a 1,5 dicarbonyl at the end. 1, 2, 3, 4. And wouldn't you know it, I did it right. So knowing those relationships after the result of these new reactions are so key to helping you double check yourself. Okay, so over here, you can see it's a Michael addition, but I just gave you the enone as the reactant. So if you want to think about what's going to happen for convenience, right? I did that to kind of be a little annoying. We know this will attack here. These swing up. We do that. So I know nothing, that double bond won't exist in my ring. I know I'm bonding from this carbon down here. Now I'm going to bond to that carbon. Whoa, lost a turned a hexagon into a pentagon. Okay, there we go. And 1, 2, 3, 4, 5. There you go. All right, so down here, a little action where I show the cuprate generation, right? So we start off with an alkyl bromide, happens to be a methyl bromide here, but then we're going to make the organolithium that we turn into a cuprate. So really what we have down here is CH3, 2 CuLi. So we're going to just basically have CH3 minus, but remember, it's not as aggressive as your CH3 minus when you have a Grignard, right? We're a soft nucleophile. We do 1,4 additions, not 1,2. So we attack here, these bounce up, then these go up. But remember, this state remains a carbonyl. It's going to reflip, it's going to taumer back to a carbonyl. So really all you've done, I will explicitly draw this CH3. I don't have to, but just for the clarity of showing you how I'm drawing this product, this is what you got. Okay? All right, gang, that is the Michael addition 1,4 addition section, okay? So last but not least, we're ending with the Robinson annulation, which is really just a Michael followed by an aldol condensation and base. Stick with me one more. I know these reactions are tough, but you're tough, so let's finish strong. Okay, gang, we have 5 total problems in this Robinson section. And yes, if you are wondering why all of these are dicarbonyls, when I feel like an introduction to the Robinson is usually done, at least in my experience, with a dicarbonyl. But if you want more, go to the next worksheet where you don't necessarily have a dicarbonyl here. You just need to have one carbonyl, and they get a little trickier. But anyways, so if you take a look here, these are the first 3 of the 5 in this Robinson section. So if we take a look up here, remember, a Robinson is just a Michael addition followed by, and I guess it doesn't necessarily have to be a condensation, but in all these examples we have heat, so this is going to be an aldol condensation in base, okay? And I guess I should have probably written this stuff down here, LDA, and then the water, OH minus, heat. Okay, anyways, so what do we have going on up here? So remember, it's the dicarbonyl that makes this proton extremely, extremely, extremely acidic. We'll get more into that in the next, when we talk about dicarbonyls and all that good jazz, but this is where you're going to make an enolate. And it's this enolate, right? It's this alpha carbon that then attacks right here. So you make a connection up there. And then, so again, it's a Michael addition, right? So you end up with a 1, 2, 3, 4, and 5 dicarbonyl. That double bond will be gone. And then after you do that initial Michael addition, right, with this double bond is going to be, like this carbon-carbon double bond is going to be, disappeared. It will be gone. And let me actually show you what that first step will look like. I'm going to keep this exactly, redraw it exactly as close to how it looks as possible. It's going to be a short isopropyl group. Okay, so it's that. 1, 2, 3, 4, 5. Okay, but then you form an enolate this way, because if you bond right here, if this is your now nucleophilic alpha carbon that attacks this carbon that I'm going to asterisk, that will form a 1, 2, 3, 4, 5, 6-membered ring. And that's the whole point of the Robinson annulation. To annulate means to form a ring, okay? And characteristically for the Robinson, that's a 6-membered ring. So it's at this point that you then create, this is your aldol condensation. So yeah, that's going to give you an aldol product. It's going to give you a 1,3-hydroxycarbonyl, but remember, we're going to drive that off. So if you want to predict this product, we so happen to have 2 6-membered rings here. So I might even just draw that. And I'm going to anchor myself with this being this right here, okay? So one thing I know I can have for sure is that carbonyl will still be here. 1, 2, 3, 4, 5. That's my dicarbonyl. And I know I have this isopropyl group right up here as well, okay? But remember, if I was going to draw this as an aldol reaction, I would have this here, and then I'd call it a day. But remember, we have heat here, so instead of taking it just to that leaves and we form our enone, alpha beta unsaturated carbonyl, whatever you want to call it. But remember, you have 1, 2, 3, 4, and 5 from your Michael, this part right here, and then from this part right here, and then the driving off of that OH, That's where you get this 1, 2, 3, 4, right? That enone, okay? So same deal here, except just honestly minus these two lines right here. It's just not a full-on ring. So again, remember, you're going to be attacking from here. You're going to form this bond right there. So if I even wanted to draw that first, I'll just do it in black. It would look like this. I know how confusing this can be, so if these were designed to not be mind-blowing, so if you were kind of hankering for more, don't worry, check out the next worksheet. This is what we have, 1, 2, 3, 4. Oops, I may have lost the carbon. 1, 2, 3, 4, 5. Sorry, I can't count. Okay, so here's what we got. And then remember, it's the second part where you form this right here. Then you attack, kick these up. So that's your new nucleophilic alpha carbon. That's your carbonyl that you're going to attack. So remember, we will form a ring. Okay? And it's this carbon, that's this up here. You can fill that in. And then 1, 2, 3, 4, 5. I know I have this there. That's this right here. I'll even put a square around it. Okay? And I know I'm kind of jumping around a little bit, but 1, 2, 3, 4. I need to make sure I don't forget about that methyl group. 1, 2, 3, 4. And then remember, we close this ring right here, and we're going to make a double bond. We're going to make an enone. There's the enone here. And on that carbon where the carbonyl was, which is evidence of where we lost it, I need to fill in that last methyl group. Okay? All right. Now, let's take a Robinson product and let's deconstruct it. Okay, so remember, so two kind of key things. This dicarbonyl right here, 1, 2, because we have it, let's use it. That's evidence of our Michael addition, right? And this is evidence of an aldol condensation. So two things I want to highlight is one, this was once a carbonyl, okay? Remember, that's where an OH would have been and got driven off. So you always want to cut the double bond. That's going to be a connection between the enone you attacked that ended up attacking what once was the dicarbonyl, and you know that helps separate two structures. Now the second thing is, where do we make the second cut? Now remember, on this side where we still have a carbonyl, there must have been an alpha carbon there that did some attacking, and that's the one I just dotted. So we want to draw this line like this, okay? So it's this piece right here that was the dicarbonyl, because that one carbon, the one of the two carbonyls disappears because it gets, you know, kicked off, and that's what happened here. So the dicarbonyl we have going on here looks like this, okay? And now we need to get the enone. So remember, so if that carbonyl will stay put, and we just have this going on right here. So remember, this is how many carbons we have left to kind of use. But remember what an enone is. 1, 2, 3, 4. There we go. So this is how we worked backwards. So cutting that through that double bond, making sure you have identified where the alpha carbon from the dicarbonyl, the original dicarbonyl, is from. You draw your line. You make sure you actually bring back that second carbonyl. If you have a situation that has two carbonyls on the thing that initiates the Michael addition, and then just make sure you break out the enone, the alpha beta unsaturated carbonyl that you attacked, and revive that double bond that disappears in that first step. Okay, gang, the first three done. Let's finish out this video and the last section with the last two. Okay, gang, for these last two, so this one was designed to kind of be annoying, designed to say, you know, you're not always going to get handed the enone and the dicarbonyl, or, you know, not always a dicarbonyl, but here we are having them in a really easy way to show the Michael and then the aldol condensation and then predict the product, live happy ever after. Sometimes it's a little bit more difficult than that, but it doesn't mean that you can't do the extra work to then get to that happy place that you're used to seeing. So if we take a look right here, we do see a dicarbonyl, we do see an enone, we see, you know, the conditions to support creating an enolate, doing a Michael addition, and then go ahead and do an aldol condensation and just, you know, finish and form our Robinson annulation product. But this looks a little troublesome. So what I want to do is kind of put it in that format that I like. So what I can go ahead and do is real quick, I'm just going to kind of sketch this down here before I erase So I think you can see that I've just worked with these 4 atoms right here, and I'll even renumber them down here. So then I just have to make sure I bring back everything I touched, or I've yet to draw. So off of the carbonyl, which is carbon 2, I have that methyl group, and then on 4 I just have a methyl group as well. So that does the trick. So what I'm going to go ahead and do is actually just redraw this in black. Okay, so I got that. And then now I want to put this in a way I'm used to seeing. Remember, what that can kind of look like is really locating this alpha carbon closer to where we're going to attack right here. So there's 1, 2, 3, 4, 5 carbons, and carbonyls on 1, 2, and then 4. So I hope you can see how this looks. I kind of just want my home base looking like this. So really, to make this carbon 2, 1, well, it's kind of aggressively long. 1, 2, 3, 4, and then 5. Okay, so just a little exercise in seeing something and, really just an exercise in redrawing things in a way that's Robinson friendly, at least the way we've been doing them here. Okay, so business as usual, right? We know this will be an attack here, right? That's where we connect here. We know that will disappear, and then we know this will do a, so we got this connection going on here, and that will give us a 1, 2, 3, 4, 5 dicarbonyl. And then this will do an aldol reaction right over here, and this will go away, but we'll have a connection here, and then we'll make an enone. So what I know for sure is that this will be carbon number 1, this will be 2, 3, 4, 5, 6, and the ring that we are going to form. So from there, I know off of 1, I just can draw this just because I know it's going to be there. It's not really going to change at all. On 2, I have a straight up methyl group. So this is 1, 2, 3, 4, 5, and 6. On 3, I have nothing. On 4, I have the carbonyl that was originally in the enone. 5, nothing. 6 is just going to have the methyl group because the bond between 5 and 6 is going to be a double bond. I'm going to draw this carbonyl a little bit more normally because that completes the enone from the aldol condensation. Okay, last but not least, I wanted to do one more like deconstruction of a Robinson product, but I wanted to make it, put it in a different way because I know these carbonyls have always been bottom left. Kind of wanted to switch it up on you. So hopefully what you can see in this, right, yeah, it appears big and scary, but it's not. What we can see, let's pick out some familiar things. 1, 2, 3, 4, and 5. Okay, cool. We see 2 carbonyls. So what I'm hoping you're seeing is, yes, we have a 1,5 dicarbonyl, and then we have this enone right here. So this is evidence of the condensation. So we must have had a dicarbonyl that initiated the Michael because we have 2 carbonyls left over. If there was just 1 carbonyl in the thing that initiates the Michael addition, there'd just be 1 carbonyl left in the product. So remember, it's this double bond that you split because that means this was once a carbonyl that got driven off. This was part of the structure that did the aldol reaction, which turned into a condensation. So split that double bond. And then remember, we have this carbonyl here, and it would have been next door that this would have been an alpha carbon that attacked over here. So split that as well. Okay, you can keep it squiggled if you'd like. So we know what we have to do, and this is the enone side because it is there's a carbonyl located there. We split the double bond, evidence of the aldol condensation. So this carbonyl being a part of the enone means that it was first attacked and then it did the attack that then drove the condensation. So what I hope you can see is I'll have this right there. Yeah, so that would be 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5 with that ethyl group off of 3. I had to put the double bond here because 1, 2, 3, 4. And then over here, just whatever's left. So we know it's going to be a 6-membered ring because 1, 2, 3, 4, 5, 6. It's on this carbon right here, that was a carbonyl. I have a methyl group over here. I have a carbonyl there because it's even in the product. And that's actually it. So, gang, thus brings us to the end. So, I hope that if there were any that were giving you trouble, they make a little bit more sense now. And if you felt good doing them and you're here just for extra validation, good job. I mean, these aren't easy. So make sure you try the next worksheet. These next problems are what I would think that you might run into, maybe hopefully a little bit more difficult, so that way you actually have to deal with this isn't as bad. But thank you for watching. If you're watching up until this point, that means that you have supported jOeCHEM. And I just want to say, you rock. I hope that jOeCHEM is helping you conquer carbon the way you were hoping to conquer it. I hope you're getting out of this tool as much as I hope you are. I'm so glad you're using it right now. I hope you're using it until the end of your organic careers. And no matter what, I hope to see you all in the next video.